Rahul came from MIT to tell us some wonders of, I guess, meta complexity.
Awesome. So thank you very much for having me. So I'll be talking about this meta complexity problem called the minimum circuit size problem. I'll be telling you a little bit about how maybe you could prove hardness for it. When I was thinking about the goal for this talk, when I usually go to a talk, I'm very happy if a week later I remember a sentence. So what I thought I'd do is I just tell you the sentence I want you to remember while I go through the talk. And my goal is a little ambitious. There are 3 parts to the sentence, but basically what I want you to take away is what is this high-level question? What maybe is the answer to this high-level question? And then one conceptual nugget. And I'll apologize to you in advance. I tried to keep this as non-technical as possible. So there's not going to be too much heavy-duty complexity theory. I'm going to try and this one conceptual nugget, I'm going to kind of try and lead you towards how you might come up with that, and hopefully that'll be interesting. If you want to talk more about technical stuff, I'm happy to talk about it afterwards. Okay, great. So, in the title of this talk, it says the minimum circuit size problem. And so I thought I'd start by telling you why you might care about it. And the first reason why you might care about it is it's going to make the next 45 minutes of your life way more interesting. You're going to lose those 45 minutes by now. You've sat down already. It's going to make it way more interesting. But I guess there are also, if you care about the mathematical reasons for being interested in this thing called MCSP. I'm going to define what MCSP is on the next slide, but I just want to give you some motivation for why you might want to pay attention. So I think what makes MCSP particularly interesting is the connections it has to other areas of theoretical computer science. And oftentimes these connections are kind of unexpected and surprising. So maybe it's not unexpected that a problem that has the word circuit in it is connected to structural complexity, but it is somewhat more surprising that it's connected to, say, average case complexity, cryptography, learning theory, and maybe not as surprising, circuit complexity. I'm going to tell you a little bit about some of these relationships. So one thing that makes it particularly interesting is somehow it's some sort of hub that connects these different areas of computer science. The other thing that makes it kind of interesting is it's a real mystery as to what the complexity of the problem is and what aspects it has. So for example, we don't know whether it's NP-complete. So unlike thousands of other natural problems in NP, we don't know if it's complete for NP, if it's complete for some other natural complexity class. We don't know. We don't know if it's hard to approximate. We don't know if it's hard on average. We don't even know a non-trivial algorithm for MCSP. So there's no Turing machine that we know of that can beat the brute force algorithm, even up to constant factors, as far as I know. What is interesting, as maybe you can guess by my color coding, is that answers to each one of these questions have ramifications in these various areas of computer science. So I'll give you a few examples. So I'm going to give you a few examples of the form, if something is true about MCSP, then that implies some solution to a long-standing open question in this area. So for example, if it's NP-complete under the usual notion of NP-completeness, deterministic, many one, and so on, you get a breakthrough in complexity theory. It doesn't really matter what this is. If you know what it is, great. But this is something that we really believe, but we don't know how to show. So, but if you could show MCSP is NP-complete, then it would imply that. If it's hard to approximate, then here I'll show that there's a worst case to average case reduction for SAT. So there's this complaint maybe sometimes people have about P versus NP, that it's really about worst case instances. It doesn't really connect so well to average case complexity. If you prove P is not equal to NP, it doesn't mean that there is a distribution you can come up with under which SAT is hard. But if you can show MCSP is hard to approximate, then you do get a worst case to average case reduction for SAT in a specific notion of average case. If you can show that some variant of MCSP that I'll talk about a little bit later, kind of like MCSP for Turing machines, is hard on average in a different notion for a different notion of average case, then we know that this is equivalent to one-way functions existing. So in this sense, it's like, this is kind of connecting the hardness of a natural complexity problem to the existence of the foundations of cryptography, which we don't really have a way to connect this without using MCSP for using, say, SAT or something. And the last thing I want to mention is that if you come up with a fast algorithm for MCSP for various circuit classes, then this actually implies fast learning algorithms for that circuit class C. If you know what, this is going to be like membership queries on the uniform distribution pack learning kind of thing, if you know what that is. But if you don't know what that is, don't worry about it. And what's interesting is that, this connection was actually used relatively recently by Hirahara to give kind of a worst case to average case reduction for this class UP. And it's used to prove a theorem that seemingly has nothing to do with MCSP. Here's a theorem that, like, can you show that UP is hard on average under some assumptions? It's nothing to do with MCSP, but the way you do it is by utilizing these kind of connections. Another result by Karmasina and Pagliazza, Kavnets, and Kolokolova actually used this connection to give a new learning algorithm for AC0 mod P. So that this was like this one best paper at CCC a few years ago. So we have these. So just to summarize, MCSP is connected to these various other areas of computer science. We don't really know a lot about it, but there are ways where if you answer the questions, then you get ramifications in these other areas of computer science. And in fact, these have been utilized in order to prove new and interesting conclusions. Yeah.
When you say things are successfully used, do you mean that these connections are like graded, as in like it's true for every circuit class and you can prove it for some circuit class, then some consequence happens? Is that what you have in mind?
Yeah, so for example, for this one, this one's approved for all circuit classes, but you might wonder, okay, is this like, I mean, oftentimes you can prove connections between things, but like maybe you can't prove the hypothesis is true, or when you can prove the hypothesis is true, the consequence we already know how to prove.
Okay.
So by successfully used, I mean, they used this connection to show something that was an open question for, I guess, 25 years or something like that. And so, yeah.
Okay, no, but like I wanted to understand what these connections, like, are these connections graded, as in like MCSP is hard to approximate for circuit class C implies something for the circuit class.
Okay.
Is that true, or?
The last case it is, the last case.
Oh,
Yeah,
only in the last-
just in the last
And
case.
the second one, there's, is, it's just for UP and.
Okay.
Yeah, just for the last one. Any other question? Okay, cool. So this is my sales pitch as to why you might care about this problem. Let me tell you what the actual problem is. So roughly speaking, what it's supposed to capture is it's supposed to capture computing the circuit complexity of a function. And so the input to the problem is going to be just a string that describes the value of a function on all of its inputs. And I want to stress, this is a really long string. Like if your function takes n bits of input, this is going to be a string of length 2 to the n. And you take it as input a size parameter s, this is some integer. And your goal is just to output, does there exist a size s circuit for f? And to be formal, I need to tell you, okay, what model of circuits are we dealing with? Just you can pick your favorite one and or not fan and or something like that. But you could consider this for various different circuit classes. Does the definition, any questions about the definition? Okay, so test. You can explain to me why MCSP is an NP. Hopefully this isn't too hard to see.
Guess a circuit and check.
Guess a circuit and check, exactly. The one thing that's a little subtle about this is that you might think, checking whether the circuit computes the functions would take a lot of time. I'd have to evaluate on all of its inputs. This truth table is of length 2 to the n, so your input length is long enough such that this like 2 to the n check is viable. Okay, great. And so as I mentioned earlier, it's a big unknown whether MCSP is NP-complete. I'll tell you a little bit about the history of this next, but just to illustrate how little we know about this problem. So this is something that I really like. So for most natural problems in NP, we know that their search complexity and their decision complexity is equivalent. And in fact, for every NP-complete problem, their search and decision complexity has to be equivalent because SAT has a search decision reduction. What's unknown for MCSP is the decision version, it's completely consistent with current knowledge that the decision version is solvable in linear time, but the search version can't be solved by any algorithm any faster than brute force search. So we really don't know how to connect the search and the decision versions of these problems. And that's kind of actually a necessary step to showing it's NP-complete because you can show that any NP-complete problem has a search and decision reduction. So it's kind of like a weird aspect of MCSP. We know for like some variants of MCSP that their search and decision complexity is related, but
it's important that S is exactly the answer.
good. We don't know, even if you allow more like looseness in there, we don't know how to you might say, can I come up with a circuit of size poly S? We don't know how to do that. We do know how to get something that's like poly S, but it's like you're allowed to be wrong on some fraction of inputs. So and this is like kind of in that case we do know, but if you want to compute the function exactly, we don't know how. Okay, great. So now let me tell you some history because one, because it's interesting, and two, because it motivates some stuff. So MCSP was first studied as far back as the 1950s. So in the 1950s, mathematicians in the Soviet Union were very interested in problems that couldn't be solved any faster than brute force. They were interested in any task which you literally couldn't do anything besides run the brute force algorithm. Intriguingly, they had a list of candidates. Probably the most prominent of them was MCSP. They were like, if you hand me a string and ask me, does it have low circuit complexity or high circuit complexity, or does it have maximal circuit complexity? Doesn't seem like there's anything you could do to solve this besides just running through all the circuits and evaluating. In fact, this guy right here, Jablonski, thought he had proved the conjecture. He claimed to have proved that you can't solve MCSP without resorting to brute force search, which would have been amazing because when he did it in 1959, it was before P versus NP was even stated. So if he had done it, he would have resolved P versus NP before it was stated. Of course, if you look at the proof, it's kind of like one of these classic I prove P not equal to NP proofs where it's like, if the algorithm has to do this, then I have to do this, and then it can't do anything like that. Unfortunately, Jablonski got into a kind of a powerful position in the Soviet science community. So it became difficult to pursue research on this problem because a powerful figure had solved the problem already. You can't, So it's kind of some interesting history. There's Kolmogorov was not very happy about this. So in the 1970s, MCSP kind of recurs again. So Levin had proved his theory of NP-completeness. Actually, he proved it because he was challenged by his roommate to find applications of theory. And so he was in order to demonstrate to his roommate that theory was valuable, he shows that, oh, look at all these combinatorial optimization problems. They're all should be unsolvable because they're kind of equivalent to this tiling problem, which was his version kind of set. But he actually didn't think the results were very interesting. He said, there's this nice blog post where he describes this, where he says, yeah, these are some cool results, but I don't know if they're worth publishing. If only I got like a popular problem within this framework, then it would be interesting. And the three popular problems he names are graph isomorphism, integer factoring, and the minimum circuit size problem. So the first two we know now are probably not NP-complete, and the third one we still don't know. But thankfully, he eventually ended up publishing his paper. He struck a deal with his advisor, Kolmogorov. He was interested in another result. He thought another result was interesting. Kolmogorov thought the NP-completeness result was interesting. He's like, fine, we'll package them together. And so this was kind of the original research about MCSP. And the motivation for this was kind of twofold. One, it's a fairly practical problem, if you're Intel, you might care about minimizing the complexity of circuits. And also it's like, has unknown complexity. Is it NP-complete? Is it not NP-complete? Where does it lie? Kind of in the modern era, maybe of MCSP research, a new motivation emerged, which is kind of hinted at in this talk, in the title of this talk, which is that MCSP has some like seemingly special properties. So for example, like if you could show MCSP is NP-complete, it kind of expands the frontier of what P not equal to NP implies. So for example, if it's NP-complete, then P not equal to NP implies SAT is hard on average. It would imply that there are no natural proofs of certain types of circuit lower bounds, implies this hardness of pack learning P poly. And maybe if this line of work completes to its ultimate goal, is maybe hoping to show that it would be equivalent to one-way functions exist. So this is kind of like the lens through which I like to view MCSP. It's kind of like expanding the frontier of what P not equal to NP is, would imply if it's NP-complete. Okay, so this is kind of like going to be the end of like the motivation section of my talk. you have any questions, feel free to ask. Okay, great. Cool. So now the question, hopefully is clear at this point, is like, okay, do we expect SAT to have these special properties of MCSP? So these special properties of MCSP that enable this average, worst case to average case reduction, or these connections to cryptography, should we expect that like all NP-complete problems have those properties? And in recent years, there's been a lot of progress on showing that variants of MCSP are NP-complete. So for example, there's a whole bunch of works here, but the one that I want to highlight, because maybe it's the closest we've gotten so far, is this result last year by Hirhara, which is really amazing. It shows that MCSP on partial functions actually is NP-hard. So what do I mean by MCSP on partial functions? You could imagine, instead of giving you a truth table and saying on all of these inputs you need to have these this output, you could have question marks in the truth table where you say, hey, I don't care. Listen, on this input, you can output anything. I just want the small circuit that evaluates to 0 and 1 on these inputs. On these other inputs, I don't care about. And surprisingly, this gives you a lot of power. And this result, I mean, like the proof is like incredible. It uses like the PCP theorem, it uses state-of-art hardness approximation, it uses from cryptography, secret sharing for monotone access structures. It uses extractable information theoretic encryption schemes. It uses the Nissan-Wigderson generator. It's really, really cool. It's this beautiful blend of cryptography and information theoretic cryptography. Sorry, it's a beautiful blend of complexity theory, information theoretic cryptography. And so the proof is really cool, but unfortunately, the gap between partial functions and total functions seems, at least right now, pretty big. Somehow, putting these question marks in this truth table lets you utilize information techniques that we don't know how to use when there's no question marks in the truth table. In particular, it seems somewhat necessary to step away from information theoretic techniques and move to computational techniques when you move to a regular MCSP. And in particular, like one kind of downside to all these results about the variance is, okay, if your goal is, hey, do these special properties of MCSP carry over to SAT? None of these variants have, for example, the worst case to average case reduction, and they don't have some of these other special properties of MCSP. So, even though these problems kind of are getting closer and closer to the original MCSP problem, it's not clear whether they're actually saying, okay, we should expect these special properties to carry over. I mean, there are problems that look very similar, like 2-SAT and 3-SAT, whose complexity is very different. And in fact, there is a barrier. It's there's a SAC-Samphenol barrier. I won't tell you exactly what it is, but it says any reduction from SAT to MCSP needs to have overcome a certain barrier, and none of the reductions so far do overcome this barrier.
But what about the search to decision?
Right.
This would have search to decision,
Yes.
right?
Yeah. This does have search to decision.
And it doesn't say anything about search to decision for.
Yeah, it doesn't. It's not clear how to take this search to decision reduction and implement it for the original one. Somehow it's like being able to put question marks in the truth table lets you. Yeah, maybe I don't have a succinct way of explaining it, but it gives you a lot more freedom to use information theoretic techniques. Yeah.
Oh, sorry. Did
Yeah.
you say that with question marks, there's like search and decision are equivalent?
Yes. So any in particular, if since this problem is NP hard, any NP complete problem is going to have a search decision reduction.
Oh,
One way to do it would be just take your problem, reduce it to SAT, use search decision reduction on SAT, and to give you the search for this.
is there a more
More direct one
More
for
direct.
this? For if you were going to replace circuits with formulas, there is a kind of nice direct one. I'm not sure whether for circuits on partial functions, there's a nice direct one. Yeah. But if you have time, I would highly encourage you to read this. It's beautiful. Any other questions? Great. Okay. So now I'm going to introduce one of the main characters of this talk, which is the random oracle model, which as far as I know dates back to Bennett and Gill. If you know better, you should let me know. And so the random oracle model is like, okay, we don't understand computation. We can't prove P is not equal to NP. We can't prove all these other great lower bounds we'd like to have. But we kind of have these intuitions as to what the computational world should look like. And one of these intuitions is that within P, there are kind of these functions which are really hard to analyze in the sense that they look very pseudo-random. And so the idea with this random oracle heuristic is to say, okay, let's just pretend in P there is just like some perfectly random function, but it's computable in P. And let's just see what happens. And so the way that this is formally modeled is you take a uniformly random function that maps arbitrary number of bits to 1 bit, and you just give all circuits and Turing machines oracle access to this function. So you can consider polynomial time with a random oracle, NP with a random oracle, and you can prove some really nice results about them. So for example, P is not equal to NP with probability 1, polynomial hierarchy is infinite, one-way functions exist. There's all this, like all things that we believe. And in fact, in this original paper by Bennett and Gill, they put forward this hypothesis. They said, for any reasonable complexity statement, and they had some definition of reasonable complexity statement, if it's true in the random oracle model, then it's true. And this was kind of later strengthened, or maybe this is the way that it's more used today. Belair and Ragave, they said, listen, if you have a cryptographic scheme that is secure in the random oracle model, then you can convert it into a scheme that's secure without a random oracle model by just, what else are you going to do? You're going to take the random oracle, you're going to replace it with a cryptographic hash function. I mean, SHA-256 looks pretty random to me, it looks pretty random to you. It should work, right? And, actually kind of funnily, like...
Very naive.
Yeah. Kind of funnily, it's like when this was proposed, this is a very abstract idea. Okay, let's take a random oracle, let's put it on the things, and things that should be true here. And now this is like the foundation of like a bunch of cryptocurrency security. It's just like it's funny how these ideas percolate over the years. And so, as I'll kind of discuss later, there are counterexamples, kind of famous counterexamples to these things. There are reasons to believe what I'll talk about later don't quite fit into this scheme of counterexamples, but for now and for most of this talk, it's kind of some model of computation. For the most part, we think it acts like the world we live in. Yeah. Okay, any questions about the random oracle model? Great. And so then now, finally, we're going to start talking about the theorem related to this talk. So there was this conjecture in this prior work, joint work with Yi Huang and Hanlin Ren. I guess, is Hanlin speaking at this seminar this semester? Hanlin Ren? Maybe you've already.
He already talks in the fall, yeah.
In the fall, yeah. Okay, so maybe Hanlin Ren. He's a great speaker. And so we had this conjecture, which is, okay, if you look at MCSP with a random oracle O, which, kind of models what we think the world should look like if you have like SHA-256, like an ideal version of a cryptographic hash function, can you show that problem is NP hard? So can you show reduction from, say, 3SAT to MCSP? So to be clear, this is like now circuit minimization where you have O oracle gates in your circuit as well. And can you show that was NP hard? And in that paper, we had shown that some variant of MCSP is sort of like which replaced functions with relations. You could show it was NP hard relative to a random oracle. And kind of interestingly, if you guys know anything about cryptography, the way that you proved that was using Macaulay's proof that there are succinct non-interactive arguments in the random oracle model. And in fact, the proof was almost like exactly that. You just take Macaulay's thing, you plug it in, and you're like, oh, okay, that shows relational MCSP is NP hard in the random oracle model. It's kind of very... So we were hoping that there would be something nice for MCSP itself. And so kind of like the main result in this paper is to prove that conjecture. And so informally speaking, it says like in the random oracle model, set cover reduces to MCSP. If you prefer maybe a more formal statement, one way to write this is that like NP is in P to the, or okay, whatever, you can read it. But this is kind of like the main result informally. And so I'll discuss some aspects about this theorem next, but are there any questions about?
Is there any intuition why random oracle should make it easier or harder or?
Yeah.
I mean, just.
Yeah. That's a good.
Maybe we should say what happens if you pick the oracle to be your favorite oracle.
Yeah, so
make it easier.
it's we'll see. We'll see why the random oracle will pop up. There'll be some like intuition I'll say later. Kind of what it's going to do is random oracle is going to give you access to some kind of very nice encoding. And that nice encoding, it's kind of it has some like cryptographic properties, and that's what's going to be exploited. But we'll kind of see why later. So maybe I'll come back and answer your question then. But in terms of if you replace this with other oracles, like the main way we use this random oracle is to kind of get this a nice cryptographic encoding. Not clear how to get that with the other things. Yeah.
It's going to be non-uniform.
Good question. It's so I wrote this here. You can either have it be like a non-uniform reduction with access to MCSP to the O, or you can have it be a uniform reduction, but then you have to give the reduction oracle access to the oracle. So you could either not give the reduction oracle access or access to the random oracle, in which case you can actually just hard code in some non-uniformity, or you can, yeah. Well, another aspect about this theorem is it doesn't show hardness for NP to the O. It only shows hardness for NP. That's because it actually uses some like non-relativizing techniques, so it's not clear how to do. Okay, so what do you get from this result? It gives like the first candidate reductions from SAT to MCSP. So if you replace O with your favorite cryptographic hash function that should act like a random oracle, this gives a candidate reduction. It overcomes this Sachs-Antonon barrier that I briefly mentioned earlier. So the way that it overcomes the Sachs-Antonon barrier is kind of interesting. It's related to like a cryptographic proof of work, like also these things that show up in cryptocurrency. We'll see kind of why later. It also works for kind of like the brother of MCSP, which is time-bounded Kolmogorov complexity. Gives essentially optimal additive hardness approximation, but gives almost no multiplicative hardness approximation. And it applies in the regime where this problem has a worst case to average case reduction. So hopefully, like we could view this as good evidence that, okay, this special property of MCSP or MCSP and its related problems should carry over to SAT. Okay, and so kind of what I'll do in the remainder of this talk is I'm going to tell you a little bit about the main idea towards proving this, which is pseudo-symmetry of information, whatever that means. And the way that this is proved is kind of combining Hirahara's work that I mentioned previously with this idea, which is pseudo-symmetry of information. So let's see. Okay, perfect. Any other questions? So just to recap, hopefully what this result will tell you is, okay, yes, probably, maybe these special properties should carry over. So, okay, so let me tell you about this key idea, which is related to symmetry of information. I'll come back to this. So in information theory, we have this very nice property that if you look at the entropy of two random variables, it's equal to the entropy of like one of the random variables plus the other random variable conditioned on the first. And this is called symmetry of information because if you apply this to both of the random variables and you set them equal to each other, it's kind of saying like the information that X has about Y is roughly the same as what Y has about X, you know, in a certain sense. So this is a very nice property of information theory. And if you look at Kolmogorov complexity, so what is the time-bounded Kolmogorov complexity of X given Y? This is like, you can think of this as like the Turing machine version of circuit complexity. If you want to measure complexity using Turing machines. So it's defined as like the length of the shortest program that outputs X on input Y in time T.
So just to make sure that for people who don't know Kolmogorov complexity, it's related to Turing machines, but not to running time of Turing machines. It relates to the length of the actual program of the code you want.
Right.
That's the description length. So there's a notion of randomness or lack of randomness or of entropy. It's just what's the shortest way to describe a long string? And this is the conditional way.
Right. Yeah. So the usual notion of Kolmogorov complexity doesn't have a time bound in it at all. So it would be like no T time here. And in that case, you know, there's no notion of running time, and you just care about the length of the program. And then the natural way maybe you add in running time is you say, okay, you have to output this description in time T. And so there's the symmetry of information property, which happens in information theory. You could ask, okay, what happens for time unbounded Kolmogorov complexity, which I'll denote with like infinity at that time thing. And it turns out there's a very nice theorem which shows that actually symmetry of information does hold for Kolmogorov complexity. It says for any string x and for any string y, you actually do have this equality up to like additive log terms. So for any two strings, kind of the information that they have each other is symmetric in a certain sense. So given these two things, you could ask, what happens in the time-bounded setting? You know, is it true that the time-bounded Kolmogorov complexity of x and y is equal to the complexity of y plus the complexity of x given y? Which roughly says that like the best way to describe x and y is just first describe one of them and then describe the other one given what you've already described. So yeah, okay. Well, what do you guys think?
Do you not have to change the T a little bit?
Oh, good question. Yeah. I'll throw that into the approximation.
Like a one-way function type problem.
Right, great, good idea. Okay, great. So let me come back to the one-way function, and that's exactly right. And let me just say, okay, if we had this thing, it would be really good for us. It's not so important that you understand why it would be really good for us, but there's some sense in which if we have this, we win. And the reason for that is prior work by me and Yang Lu and Raphael Pass had shown that like this conditional problem actually we know is NP hard. If we know that if this problem is NP hard and symmetry of information held, then we can approximate this NP hard quantity using computing time-bounded Kolmogorov complexity, which if you squint at it looks like maybe like MCSP. So if symmetry of information did hold, then you know, we could maybe prove the NP hardness of MCSP. But as you pointed out, you know, maybe symmetry of information doesn't hold. In fact, if you consider this example of a one-way function, so how many people here are familiar with the one-way function just by showing it? Okay, great. So a one-way function is a function that's like easily computable in one direction, but maybe not so easily computable in the other direction. So let's just examine the case where it maps like n bits to n bits. So it's going to be usually is referred to as one-way permutations. So it's very easy to, you know, compute from x, y, but it might be very hard to go back in the other direction. So like the classic example is you take two integers and you multiply them together, two prime numbers, you multiply them together. You know, multiplication is really easy, but maybe inverting, but we don't know how to factor quickly. Okay, so if I have a one-way function, then you know, to get symmetry of information, we would need that this to roughly hold. So okay, well, let's say we just pick x uniformly at random, then we apply f to it to get y. What should we expect maybe kt of y to be? Let's say it's like an injective function or something like that. Yeah. So you probably expect it takes like n bits to describe x. You applied like, let's say, an injective function f to it. F to a uniformly random thing is going to be a uniformly random thing. So you kind of expect this to be n. Oh, I guess I was going to do this first. Okay, but this is going to be n. And now, spoiler is revealed. What is the complexity of describing x and y? Well, I mean, okay, x is uniformly random. You know, there's nothing you can do there. Just describe it. And then once you have x, you can get y by just applying f to it. Maybe that adds like a constant term. Let's not worry about that. So we have n on this side, we have n on this side. And now here's kind of the crux. How about describing x given y? So x is the uniformly random thing. Y is what happens when you apply the one-way function to it. How many bits are you going to need to describe x given y?
And to the epsilon.
Yeah, exactly. Depending on how strong your one-way function is, you might think that this is like close to n, because you know, in some sense, y has all the information about x in information theoretic sense, because you could always, if you had an unbounded amount of time, you could go back and invert and get x. But if you only have time t, you know, not clear how to do that, and so maybe the only thing you could do is n. So what we expect to be the truth is that this on this side it's n, and that's 2n, and those things are not close to each other, we'll say. And so symmetry of information fails. And so the key idea of this work is asking, okay, can we fix this? Okay, we have this problem, which is that symmetry of information doesn't hold because of the one-way function example. Is there some way to get around this? So maybe I'll let you think for a little bit, like how could you try and fix this? And if you have any ideas, feel free. You want that these two quantities are approximately equal. The problem is that if like y is the output of a one-way function given on x, then like you're gonna get 2n here and you're gonna get n there. How could you try and fix this? So I don't know about you, but in elementary school, I was told this quote, which is if at first you don't succeed, try again, which in my life hasn't been very useful, but there is a related quote that is very useful and very useful in computer science. And that is, if at first you don't succeed, try encoding differently. And that's going to be kind of the key idea for this, which is to say, okay, symmetry of information fails, but I'm going to try and fix it by encoding differently. In particular, I'm going to try and come up with an encoding y tilde of y such that this holds, which is that the complexity of x and y tilde is roughly the complexity of y tilde plus the complexity of x given y. So what I mean by an encoding of y is I mean there is some efficient way to go from y tilde back to y deterministically. But y tilde might have some extra information in it. You know, it encodes y, but it might have a bunch of other stuff in it.
It could be X, but it doesn't have.
In the
Yeah.
one-way function example, it could be.
In the one-way function example, it could be x. Yeah, but it might not help you. Yeah. Good. So this is going to be the key idea. And if we get pseudo-symmetry of information to hold, then you can, I'm not going to tell you all the details, but from that somehow you can pull back and get hardness. But so we're just going to talk about pseudo-symmetry. Okay. So this is like the last thing I want you to take away. Everything after this is just icing on the cake. Yeah. Yes.
Can I ask you, so what's going to be the complexity of this y prime actually? In that picture, like you said that it's going
Which
to
is
be
going to get smaller? The Kolmogorov complexity of y prime tilde or the conditional?
Good. So what's going to happen is that complexity of y tilde is going to get higher.
And then you want
You
to
want the right hand side to be smaller.
So
x y tilde will be high.
Oh, x y tilde is gonna be high.
okay, maybe I don't understand the question. You're saying.
Yeah, well,
Are the numbers?
yeah, which will go?
Oh, I see. So this is going to become x y tilde is going to become like 2n. Yeah. Sorry. Yeah.
Can you say again, I don't know if you said, how is this related to MCSP exactly?
Good. Let me recap that. Okay, so there's a couple misdirections that I need to tell you. So the misdirections are MCSP, squint at it, it's this guy, right? I mean, it's like they're two different problems, but maybe one's the Turing machine version of the other.
But the input y, I mean, there's this condition.
Sorry.
Rather than wanting to know the circuit complexity of the string, which is a truth table you asked about, it's Kolmogorov complex.
You think x to be a bit, the output, and y to be a random string, or?
Yeah, so sorry, I should have said, if y wasn't there, then this is like the Turing machine version of MCSP.
Okay.
Yeah.
Oh, so x is like the truth table.
X is like the truth table, yeah. So that's the first bit of misdirection. And then the second bit of misdirection is saying, okay, let's say symmetry of information did hold. Well then by some magician has come down and told you that this quantity is NP hard to compute. And then, well, if symmetry of information did hold, then I could subtract this guy to that side and then estimate the NP hard quantity using the quantity without the conditional part of the thing. And so then that would say, okay, because this guy is NP hard, this guy is NP hard. Does that answer your question? Yeah, I'll come back to bringing this back to MCSP more towards the end. Okay, good. All right, so just to recap, symmetry of information held, that would be great. It doesn't hold because one-way functions exist. And so then our trick is going to be somehow encode differently so that we do get symmetry of information. Okay, good. All right. Okay, let me before I tell you what's next, or actually let me tell you what's next. So we have this one-way function example. So just to recap, you go from x to y. We had that this n is not equal to n 2n. Now what we're going to do is we're going to add another step in the process. You're going to go from x to y using the one-way function f. But now there's going to be this encoding step. So there's going to be some function encode, which takes as input maybe a lot of randomness. Think of this randomness maybe like y and y tilde are length like n and n squared, and like r is of length n to the 100. A lot of randomness. And so you go from y to y tilde. And then there's also going to be a decode function, which will always with 100% probability take you from y tilde back to y. That's why I call it an encoding. And now our goal is to pick an encoding function so that this will approximately hold. Now, one direction of this is actually kind of easy, like because the decoding function always works, you can always describe x and y tilde by first describing y tilde, and then describing x given y, you're able to go from y tilde to y. So anyway, I haven't said anything very interesting yet. Just that because of the decoding function, one of these directions is hard. So the other direction is really the difficult part that we need to try and figure out. Does anybody have any guesses as to what you might do?
Can you use R as an error correcting code?
Oh, okay, interesting. So you're saying take y, error correct it. Okay, so you're saying how are you saying it again?
I was just thinking of R as a description of a code and applying it to Y.
R is the description of code and then applying it to y. I see.
You need some hardness, like why tilde is supposed to be computationally harder to describe if you want the inequality in the other time.
Yeah, right. Like you want.
A code if it's efficiently computable will not work.
But I guess.
Random code.
Oh yeah. You're right. But then okay, so then you're gonna then what's your decode function gonna be? Are you going to because if you just encode with a random code.
Yeah, that's the hard part. Yeah. Yeah, the decoding is hard.
Decoding is hard, yeah. Okay. But a good idea. It's
For efficiency of the encoding, yeah.
yes, yeah. Do you need efficiency of the encoding? Well, you'll need efficiency of the encoding so that the reduction works, but you don't really care. It could be like an arbitrarily large polynomial, but you'll want the decoding thing to be relatively.
But this would use the order, presumably.
Yes,
So it's not really efficient.
Yeah, that's true.
So some independence of y tilde and x, or
Yeah, kind of what you want to do is you're like the way I envision this is somehow like you want to add in like so many extra bits of information, like just random bits of information into y, so it's that you kind of destroy the nice connection between x and y. So it's like kind of like some sort of independence thing. But the fact that you can always decode back to y, it's hard to say this is like truly independence,
Decoding will also use the order.
Decoding will also use the word. Okay, so just to recap what our goal is going to be, if we're like just looking at the one-way function example, which is going to be our running example throughout the talk, our goal is to have this hold, which basically, if you like look at it, we're going to want this to be like this quantity here to be like n plus length of y. Is what we're going to
The
be.
outer can tell you, for example, which of the bits of y tilde is hiding y.
Which of the bits it could potentially tell you that. It could potentially tell you that, yeah. Okay, and so what we're gonna end up using, kind of like the key property of computation that enables this encoding decode. Like you might look at this and be like, okay, symmetry of information fails. Why should encoding or decoding help at all? I mean, it doesn't seem like that should really help. But somehow fundamentally, the thing is that there's in the information theoretic world, pseudo-randomness and compressibility are the same. Or randomness and compressibility are the same. But in the computational world, pseudo-randomness and incompressibility are not the same. It's kind of like, if you're familiar with it, there's like Yau pseudoentropy and Hill pseudoentropy. and they're different. So somehow it's going to be exploiting this. If that didn't make any sense, don't worry about it. But the fundamental, this kind of is the key point.
You are exploiting the very issue which is your problem.
Very issue that is my problem.
Your problem is the one-way function exists, and
Yeah. We're exploiting
you got into a problem exactly because of
exactly
the
because of this.
and
Yeah.
you're using it to get out.
Yeah. Oh, that's very nice. I never thought of it. Okay. So what encoding? So here is my intuition when I was thinking about this. My first intuition was, okay, maybe I should it was kind of along the lines of this coding thing. It was saying, okay, let me let y tilde just be an encryption of y using some secret key. I'll pick a random secret key, I encode it, and then what I'm going to do, or I encrypt it, and then I'll let y tilde just be my encryption concatenated with the secret key. I was like, so then, since I've given you the secret key and the encryption, you can decode back to y. But maybe this encryption should be really nice. It should be like an ideal encryption thing. And like maybe it'll play really nicely with this. That was just my intuition. And I thought, okay, let's what's like the best possible encryption scheme? It's like Shannon's one-time pad. And what's the one-time pad? We'll just throw that in the random oracle. And let's see what happens. So here was the attempt. You pick a bunch of random strings R1 up to Rn, and then you'll one-time pad Y. So then you'll XOR the first bit of Y with the output of the random oracle on R1, XOR the last bit of Y with the random output of the random oracle on Rn, and you let Y tilde be that. And now let's go back to our one-way function case and see what happens. Our goal here is that we want the description length of x and y tilde to be the length of y tilde plus n. And if you look at this, like if R1 up to Rn are, oh, what did I do? Did I do n-bit strings? Yes.
So it's not
Should be answered.
and squared plus n.
Oh, yeah, what did I do? Oh, you're right. Sorry, my bad. This should be like n plus n squared. Good, my bad. This should. Yeah, so this should be 2n plus n squared is what this should be. Now, what's the true value you get here? The problem is that there's a better way to describe x and y tilde, and that's as follows. You describe x, that'll cost n bits. Then you'll describe all of the random bits R. And now the point is, you never. Right. Now you have all the information about y tilde because you'll know R1 up to Rn. You know x. From x you'll know y. And so you can just produce the whole string y tilde. Because you know all the bits of y and now you know all the bits of R.
It's again a gap of n, even
Again.
though you have n squared in the.
Yeah. Good. And so now you'll get this. Oh yeah, I did this wrong. But then you get off by an additive n. So this doesn't work. And so then you're like, okay, this didn't work. You're like, okay, so this idea of just putting like the secret key at the end, like that's not going to help because if you put the secret key at the end, then you'll just take x, you'll find y, you have the secret key, and then you'll just encrypt it. So it's like, it's not giving you the gap you want. So the first attempt doesn't work. And so you look at this for a while, and then you're like, okay, how do we fix this? Does anybody have any ideas? What might be a better encoding scheme?
How long did it take you?
It took me, I think, an hour to come up with the encoding scheme and 2 months to prove that it worked. But it was a guess. It was a guess, and I think it wasn't even a good guess. It was a lucky guess. But yeah. Okay, so then the second attempt was a random pre-image. I was like, okay, forget about this XOR thing. right? The XOR thing didn't seem to help. I don't want to have an encryption kind of thing. Let me instead have my oracle be an oracle from lambda bits to 1 bit. And what I'll do is I'll set y tilde to be the invert, to be a random preimage of each of the bits of y. So I have the bits of y, y1 up to yn. I look at the oracle and I'll just pick, using rejection sampling, a uniformly random preimage of 0 or 1, depending on what the bit is, and I'll let y tilde be that. Is the definition of y tilde clear? Okay, now let's look again at the one-way function case. Again, now, remember the goal is to get n plus length of lambda tilde. Then now that's gonna be n plus lambda n, because it's gonna be lambda bits for each bit of y. Okay, so anybody have an idea as to how you can upper bound this? So this is not gonna work again. So that means you can get an upper bound that's better than n plus lambda n. Anybody have an idea?
Could you just describe the preimages? Could you just get one?
So you're saying, let's just, if you describe each of the preimages, but that's going to give you length of lambda tilde, right? Is that, oh, okay, so, did I misunderstand, or?
Oh, maybe.
Someone raise their hand, or? You're along the right line, so you want to describe all these prefixes, all these preimages, but do you really have to describe the whole preimage?
Well, one, you can save a bit in each, yeah.
So you say, okay, I have my x. What I'll do is I'll describe x that costs n bits, and then I'll know y. And what I'll do is I'll describe the prefix, or sorry, the preimage. But I don't need to describe the whole preimage because I know what the output is going to be. Because if I know y, I know, I know what the output of the oracle is going to be. I know it's going to be either 0 or 1. So in expectation, I can actually save half a bit. Because I already know the output of the oracle, so I describe the first n minus 1 bits. If there's only one of the remaining 2 bits, which outputs the right answer, then I don't have to describe the last bit. Otherwise, I have to describe the last bit. It's a random oracle, so half the time I should get this. So now I'm off by an additive n over 2. So at least I've shaved something by 2, but this is still very high. And in particular, it's not clear how to get like much better than this n over 2. But like you might be like, okay, I saved a half now. Maybe I can do something slightly smarter. Oh well, I mean, there is something you can do, which is attempt number 3, which is going to work. But yeah, okay. So now there's just one more idea, which you have to add to make this work. Anybody have a guess as to what that idea is? Oh, so this doesn't work. Good. So it turns out the problem with this thing, okay, what's the attack? The attack is I tell you a prefix of the preimage, and then you can go in and check and pick the one prefix which has the right answer. But this attack requires, evaluating the oracle in expectation on two values. Evaluating the oracle on 2 values. What if you have to make it so that you have to evaluate the oracle on more values? So instead of looking at the preimage of a single bit, you break y into chunks of size lambda and then pick a random preimage. And then this attack becomes more expensive because, figuring out the right answer would require maybe like 2 to the lambda thing. So now the attempt number 3, this is the one that's going to work. We're going to do a random preimage of a lambda chunk. So now let's pretend we had a random oracle that maps lambda bits to lambda bits.
Lambda will be like into the epsilon.
So it depends. Actually, in the proof, we can set it to even like C log n for a sufficiently large C.
Just one.
Because of the hardness of approximation, but like you might think a priori you want to set it to n to epsilon. Yeah. So now you'll set y tilde. You'll break y into chunks of size lambda. So now there's n over lambda of them. You'll pick a random preimage of this. Now, if using rejection sampling, this is going to run in like time, like poly t to the lambda. This is why we want to set lambda to be like O of log n, so that the rejection sampling runs in poly time. Also, if you're familiar with cryptographic proof,
I don't understand, you're using the oracle just on length login.
yes, yes.
It's
Yeah.
really a random string, polynomial size, you don't really need a random oracle, you don't.
But you need
never-
that string of, a random string to poly size to have small circuit complexity. And so this is like a proof, also like a classic cryptographic proof of work where you say, okay, I want a string with X numbers of zeros in front of it or something like that. And that should take time, like 2 to the number of zeros or something like that.
So let me ask you, so if you go actually from lambda to lambda, so do you really go from lambda to lambda exactly?
No, I think we go from lambda to 2 lambda or something like that.
So like
I think lambda to 2 lambda is what.
lambda to,
Maybe 3 lambda, I'm not sure. Is there a reason you would ask that question? Or?
well, because random oracle actually may have no preimage if you go from lambda.
Oh, right. Yeah, good. Yeah. Sorry, my bad. Yeah. In order to have a preimage, we want 3 lambda. I just didn't want to add another number, but that's a good point. Okay, so now in the one-way function case, this string, because we take each of the lambda chunks and like map it to another lambda length string, we're just going to have something of length 2n. And the best bound you can get on this using the attack described earlier is like something like you shave off log t number of bits, because you describe the preimage up to a certain number of bits, and then you have to, and if you have like k bits left over, the time to run the attack is going to be like 2 to the k. So the number of like bits you can save is like related to log t.
So for you, t will not be polynomial time, but like time n squared or q.
Yeah, t will be some fixed polynomial.
It's polynomial.
Well, if you think about it, it's like it'll have to be a fixed polynomial for the definition to make sense, because like the time bound needs to be like an absolute number, right?
Yes, although you allow fast factors in the right and left, right, I mean, the goal stays there.
Oh, I see.
You asked, it's not the same t.
Yeah.
But it will be small factors like 2 or 3.
It'll be some fixed factor. Yeah, exactly. And so then what'll happen is we want to set lambda such that like t is much less than 2 to the lambda, and then this will work out. And I mean, it's not totally clear. This is just the one-way function case. There's all sorts of other cases, but it turns out that you can prove something like this whole. And wait, before I go on, were there any questions about this? So kind of the intuition is, you're going to take y and you want to encode it in some way such that encoding looks really random, which is what kind of this preimage of a random thing of a chunk, that's going to look really random because O is a random oracle. But you also want it to be hard to compress without using a lot of time, and that's what this chunking is doing for you. Because even if you know the right answer, even if you know what it decompresses to, it's still hard to. Or know what value is to, it's still hard to compress. And this is actually precisely where you have the difference between pseudo-randomness and incompressibility. Because like, if you think about y tilde, it's a very not pseudo-random string. Like, because if you evaluate the oracle on any one of the pieces of y tilde, it's giving you a fixed answer. It's giving you the value of y, but it is incompressible, basically because of this argument. So it's like, the distribution on y tilde is highly not pseudo-random, but it is incompressible. Yeah.
Isn't the loss still a constant factor of n?
Yes, good. The loss is still a constant factor of n if you set, lambda to be O of log n, as I was saying. But this is actually tolerable in the hardness of approximation because it can be an arbitrarily small. Yeah, it's not clear that this would be enough, but you have to, if you work through the other stuff that I handled.
So you get the goal within n to the epsilon, that's what you're saying?
Get,
It seems more like epsilon n.
yeah, it's going to be epsilon n.
Epsilon n, and that's enough.
Yeah, and for sufficiently small epsilon, and that's enough, yeah. Because the hardness of approximation on the other side is like multiplicative up to even log n factor. So Well, okay, you really care about, okay, let's not get into it, but it's enough, it's enough. Maybe it's surprising, but it's enough. And so using this, you immediately get, or okay, with a lot of work, you can show that symmetry of information holds for time-bound Kolmogorov complexity with a random oracle. And from that, you can get time-bound Kolmogorov complexities hard in the random oracle model. You need a completely different, well, you need a different approach for MCSP because like, even the idea of symmetry of information doesn't make sense for circuit complexity. It's kind of like trivially false. Don't worry about that. But somehow the ideas used in here can be applied to make it work for MCSP, but you need a little bit of work for that.
Do you know, I mean, just about the fact that you get only epsilon, and do you know that you can also get into the epsilon or even polylog in the using a random oracle? I mean, it's an independently.
Yeah.
Interesting question, huh?
Yeah, I don't know. I never explored that. That's an interesting question. Yeah.
Right. No, you're not using any recursive structure, or you are not using.
Yeah. Okay. And so let's see. So I'll just briefly say what the reduction kind of looks like. This is like what the actual reduction looked like. All this time I've just been giving you intuition about the proof. The reduction from set cover kind of looks like this. You're going to have your set system that you want to show reduced to some string complexity. You're going to generate secret key.
You say what set cover is just.
Oh, okay, yeah, good. Yeah, maybe I should be like, because I guess I'm 2 minutes over. Maybe should I end it or?
You can talk for another 7 or 8 minutes.
Okay, I mean, I don't want to keep any.
That's okay. You are keeping, but we like it sometimes.
Okay. Okay, so the set cover is this problem where you're given a bunch of subsets of the universe. The universe is 1 up to n, and your goal is to come up with the smallest number of sets whose union covers the whole universe. So our goal is we want to reduce set cover to MCSP. So we take in a set cover instance, and we want to output the truth table of some function. Somehow the circuit complexity of that truth table should be related to the minimum number of sets you need to cover. So what we're going to do is for each set in the system, so we have S1 up to SK, we're going to generate some sort of secret key for it. And you should think about secret key in terms of like one of these encryption schemes. Then what will happen is you'll pick random messages for each element in the ground set. So there's these elements in the ground set 1 up to n, and you're going to pick like a random string to associate with each one of those elements of the ground set. So far we have secret keys, which are associated with sets, and random messages, which are associated with elements of the universe. And you should think about the messages in terms of things that can be encrypted using the encryption scheme associated with secret keys. And now what you're going to do is basically whenever an element is in a set, you're going to encrypt its message using the associated secret key for that set. So messages correspond to elements and secret keys corresponds to sets. So naturally, what are you going to do if an element is in a set? You're going to encrypt it. So you're going to get some ciphertext associated with it. And now this is kind of where the magic happens. This is sort of related to pseudosymmetry of information. You're going to kind of come up with a nice encoding of that ciphertext, which is, I'll denote by like EIJ.
You're going to describe a truth table of a function. So where do we see here a truth table of a function?
Good, that's output. So now what you're going to do is you're going to output a string it's basically a truth table that is like the concatenation of all of these encodings and the messages. So basically this is going to correspond to a function where like you take as input like some index and you want to output like a bit of the concatenated version of all the encodings and all the messages.
I see, but this is a polynomial sized message, right?
This is going to be a polynomial sized message.
So you're scaling down your definition of MCSP, but so.
Oh, I see. Yeah. So you can think of like this n is going to be like 2 to the n of that. And now kind of it's going to be hard to see exactly why this works, but at least in one direction, the idea is that a circuit size upper bound you could get is you could just memorize all of the encoded values and memorize the secret keys corresponding to secret keys in an optimal set cover. And then you don't have to memorize all of the MI because the encodings, they encode ciphertexts If you have the secret keys, you can go from the ciphertext back to the messages. So if you have to memorize all the encodings and all the messages, instead of memorizing all the messages, you could just memorize the encodings, memorize corresponding secret keys, and then you can decrypt to get back to the messages. So that kind of tells you, okay, maybe the circuit complexity of this is related to the number of secret keys in optimal set cover. And then you have to do a lot of work to show the lower bound. That's kind of the idea of reduction.
But it's something more the Kolmogorov complexity description. It's all about description.
Yeah.
The circuit is trivial.
Yeah.
And the things you keep and the things you
Yep.
forward.
And okay, so this is my last slide. I mean, next one's open questions. But if you have any questions about the reduction, obviously this is very high level. Okay, so thank you for listening. So I'm going to be around today and tomorrow. I'm happy to chat if you guys are around. And there's some nice open questions related to this, but thanks for listening.
Questions?
So
Yeah.
are this question related to the third point here? Like if you get much better than the epsilon n loss, would you get multiplicative hardness or?
Yeah, so kind of the way that I've described the loss is additive. If you somehow get something in that pseudosymmetry of information thing that was like a multiplicative approximation to that, you would be. I'm not sure that that's, I mean, it's possible. I haven't thought about getting better additive hardness approximation, but multiplicative thing seems quite hard to do, but I'm not sure.
Yeah, you don't see them in Kolmogorov complexity.
So what's a better assumption than a random oracle? Like,
Good.
what's the next step?
Yeah, so like, I mean, ideally, or one better assumption would be like take some standard cryptographic assumptions, which like sort of they imply like pseudo-random functions, but they don't imply like random oracles or something like that. Something like that. So ideally, it would be something that's like an assumption that's been made before in cryptography and is believed to be instantiable in a formal sense. Like with random oracles, we think we have like informal instantiations of them. They don't have all the properties of random oracles, but like all the nice properties or all the natural properties of random oracles maybe you expect of them. Yeah. Okay. But there are other cryptographic assumptions which we think are like truly instantiable. Like I mean, one-way function, for example, is something that we have candidates that we think have all the properties of one-way functions. There are no candidates, or in fact, it's impossible to have a candidate that has all the properties of a random oracle.
Is there a good reason to think MCSP is not in current? It seems like you might be able to prove that something doesn't have small circuit. That's what we're trying to do a lot of the time.
Right. So there are so people have made these conjectures that it's hard to prove that a random function has large circuits.
Not just a random function, it's a given function. It's a large circuit. This is used in proof complexity.
Yeah.
In weak proof systems, you can actually prove such low bounds and it's a standard, it's like Figural principle. It's another principle in proof complexity. This function has no small circuit. And so this I think is the reason I believe that's not in concrete.
So we think that for random functions, there shouldn't be small proofs.
Yeah, but in the situation you are given the function and you say it does not have a small circuit, prove it. If it doesn't have a small circuit, certainly you cannot prove it. And otherwise it seems like a hard tautology to prove.
So there's no collapses, like if it's in current P, then something bad happened.
No, I don't. I mean, I would refute like a bunch of these conjectures related to the random functions one, for example, but nothing bad happens. In fact, it's a great world for us, I would say, because I mean, we don't know how to prove lower bound on one function. If it's in co-NP, then there exists lower bounds for every function, which would be amazing. I would expect that it's not in co-NP, but it would be amazing. It would be I hope that it is in co-NP. I don't.
I mean, you might not be able to find those proofs, but
right. But at least that'd be better than our current. Well, okay.
Does this result strengthen your belief that MCSP is unbeatable?
Yeah, I think it, I mean, no,
You know?
it's personal, it's a personal question, but,
Yeah,
yeah.
it's a person. Yeah, we do everything. Uh, Yeah, so why? Because you believe SHA-1 is like a random walk?
Yeah, actually, I do believe that SHA-1 kind of looks like a random oracle. I guess it's funny. It's like these days, I guess I've been talking more with cryptographers and like the belief in the random oracle model. It's like is to some extent very strong, and I think I've been sold on it. I've been indoctrinated into the cult, but before I didn't know what a reduction to MCSP would look like. You know what I mean? I didn't know. I mean, we had these other reductions, but they're kind of crucially using some aspects. And at least now it's like, okay, I know what a reduction can look like. And I think for natural candidates of like things like SHA, it should work. But I don't have a proof of that. So to me, I always believed it was NP hard, so it's hard to say. It's increased my belief, but at least the fact that I can now think about, okay, what would a reduction might look like is very satisfying to me.
I guess during the talk, you mentioned that there were counterexamples to the
Okay.
random oracle religion.
Yeah. Yes, yeah. So there are famous counterexamples. The most famous counterexample is IP equals P space. So it's known that, with no oracles, this holds. But on the other hand, if you put a random oracle on this, it doesn't hold. So we know with like probability 1 over random oracle that IP is not equal to P space. Although, in this algebraization paper, fundamentally the problem in this case, the problem is this. What is the point? So I have a random oracle, and I give you access to the random oracle in order for you to compute it. The idea is I'm supposed to make it look like that this is an easily computable function. But fundamentally, the problem here is that there's some property of easily computable functions that is not being preserved here. In particular, any easily computable function has the property that a low degree extension of it is also an easily computable function.
That's not possible.
But can't you take the circuit and then
It's an exponential extrapolation, right? I mean, it requires exponential time to compute it on other values in the field beyond 0. At least the obvious way is required. I give you a function on NP, it's on 2 to the n values of the Boolean function. So it's a multilinear function.
right?
But I want you to compute it on, inputs that have 2s and 3s on them.
Mhm.
How can you do it? I mean, it seems like you have to do interpolation and the polynomial is. I mean, if you
Can't okay, anyway, let's maybe okay, but fundamentally the problem here is that like there are when you use IP equals P space, you have all these algebraizing techniques. And with this random oracle, you can't algebraize it because you only have access to the original function.
Yeah, in P space you can do it. That's the point. Yeah, I mean,
Yeah.
It's not efficient.
Right. Oh, yeah.
In P space you can interpolate it's a multivariate polynomial, of course, but not.
But not in
P. Efficiency is exaggerated.
Good. Yeah.
But you also require that for that inequality. Well, like for IP to not.
Yeah, you need it needs to be proved. But I'm just saying the side that's easy is that in P space you can, and that's used all over the place.
Right.
You can compute multilinear or low degree extensions in P space. Let's use them.
Right. So
I don't
fundamentally,
know how to take an NP problem and compute this multilinear extension in the hierarchy.
right. And if we were able to do that, we would get worst case to average case reduction and all these nice things.
Also, when you say probability 1 over the random oracle, you don't literally mean 1, right?
Yeah. And so I do literally mean 1, but in like it's like a measure theory sense, you know what I mean? Because it's like a random oracle has like an unbounded number of inputs, so it's like really like a measure theory kind of. Does that make sense? It's like
And the input size runs to infinity. I mean,
I see.
yeah.
Maybe lambda, like.
Yeah. So when I talked about, sometimes I called it lambda to lambda, but when I say probability 1, that was in reference to having like a random oracle with an unbounded input length.
But
Like
it's
you
not
said.
important. I mean, you can think point blindly.
So this,
Oh, yeah.
so this reduction holds with probability 1 over random oracle. Yeah, there's this nice rule, it's called, I think it's like Homogorov's 0-1 law, which basically implies any complexity theory property is going to hold with either probably 0 or 1 relative to random.
All right. All right, thanks.